Hi everyone, welcome to this introduction to Calculus 1. This is the third lecture and we will continue with the derivatives. So to summarize what we did last time, we introduced the derivative. And so we saw that the derivative of a function f at a point x is in fact a limit, and it's defined by this formula. So when this limit exists, we say that we can derive the function f, and the derivative of f at the point x is called f prime of x. Now, from this formula, you can compute the derivative of various functions. For example, we saw that the derivative of the function x squared is 2x, and the function of square root of x is 1 divided by 2 square root of x. All right. So what we are going to do today is work with examples, and we are computing various derivatives. So it's the 5 and its example. So you add an assignment to do, and that's basically what we are going to do today. So let's start with a first example. For example, if I want to derive the function, let's say 4x5. So by applying formulas that are known for derivative, I can compute this derivative, and it will be 20x to the 4. Because when I have a number a times a function, and I take the derivative, I know that this will be a times g prime of x. And as we saw, the derivative of x to the n, when n is a natural number, is mx minus 1. So that's it. So f prime of x, if f of x is 4x to the 5, then its derivative f prime of x is 20x to the 4th. All right, so this is my first example. So if you want to interrupt me, don't hesitate. We can spend more time in explaining. So if there's no questions, I move to the next example. I call it B, and let's say f of x is equal to 3 divided by x squared. Okay, so to compute this derivative, in fact, the formula that we saw previously applies. So I can write that f of x is also equal to 3x to the power minus 2. Okay, this is the same thing. Now, if I compute the derivative of x to the power minus 2, it will, I can do the same. So I apply this formula and it will be minus 2. This is the minus 2 here. X, and here I will have minus 2 minus 1. Okay, so this is analogous to x n prime equals n x n minus 1. In fact, this formula applies not only for natural numbers, but also for negative numbers, right? Okay, but since I add these 3, now from that I deduce that f prime of x equals 3 times minus 2x minus 3 equals minus 6x minus 3. Because again, if I have a function a j of x with a is a real number and g a function, then the derivative of aj of x is a j prime of x. Any questions? All right, so again, what we are doing right now, from the definition of the derivative, you can prove that typical functions have derivatives. There are formulas for that. So you can, I put in the material some documents where we can find this formula. So we are just going through some examples to apply those formulas. Next example, see, let us assume that f of x now is what is 3x times x4 plus 7. So I could also write this as 3x5 plus 21x. So in fact, I could use this this expression to compute the derivative. It will be simpler, but here I want to compute a product of derivatives. So I'm going to use this expression to compute the derivative, and then I will use the other one, and hopefully we will find the same thing. We have to. So there's a formula for the product. So if I want to compute the derivative of x, this is the formula. I take first the derivative of this function, which is 3. This is a linear function, so the derivative of a linear function is just the number. It's the slope, in fact. So it's 3. Then I multiply it by this function plus, now I take this function and I multiply it by the derivative of this function, which is 4x to the third, and that's it. Okay, so in fact, the derivative of a product, if I have u v prime, it's u prime v plus u v prime. So I just applied this formula. So now it's just computations. So I will get, so let's do first the x to the fourth. It's 3x fourth plus 12x fourth. So 12 plus 3 is 15. So 15x fourth plus 21. All right, so in fact, I could use also this formula. So the derivative of the sum is the sum of derivatives. So I could use also directly this expression to find. So the derivative of 3x5 is 3 times 5, 15. X 5 minus 1 is 4 plus 21. So I found the same thing. So two things that will be very useful for you the next years to come is, okay, this formula here, and of course the more basics computations that are here. Any questions? So again, this is an introduction to Calculus 1. If you want to master that, you have to exert yourself. You have to do a lot of computations like that. And after you will see also more functions, more specific functions. But let's continue with other examples. So I'm here, right? So let's add here some. No. 21, right? Yeah. All right. So the next example is, so we do the product. So now we are going to do, I'm at a D, fourth example. The first example is, oops, D. Let's compute f of x equals 3x 4 divided by x to the 7 plus 5x squared plus 1. So for the product, the formula is u v prime is u prime v plus u v prime. So again, you can prove that with the definition of the derivative that we saw last time. This is a conclusion that you get from the basic definition of the derivative. So you have no choice. That's it. That's like that. There's laws in physics and also in mathematics. And when you have the definition of the derivative of the product is that. It's not from the, when you look at it, you could say u v prime equals u prime v prime. No, that's not right. So if you go back to the definition and you compute limits of u x plus h vx plus h minus u x vx divided by h, when h goes to 0, you will obtain that. Okay, I'm not doing here because usually proof are left as appendixes in calculus courses. So you first have to assimilate, to work, to do exercise with the formulas, and then you can go to the proofs. So in the same way, there's a formula for this expression, u divided by v. So if I want to compute the derivative of a function u divided by a function v, again, you could think that this is, but this is not, right? That's not the case. If you do this computation here, as the definition of the derivative, you will find that you have this formula. So it's u prime v minus u v prime divided by v squared. Okay. So what we are going to do is just apply this formula to our function f. So if I do that, So let's write again f of x. F of x is 3x to the 4 divided by x 7 plus 5x squared plus 1. And so f prime of x, if you remember the formula, you can write it here. U prime v minus u v prime divided by v squared. What I'm going to get is, so I need to compute this derivative. This is what? This is 12x to the third times everything times this function, which is the v. All right, then minus, okay, I just wrote here this part, minus u and v prime. So v prime is 7x 6 plus 10x, and that's it. Divided by v to the square, which is just x7 plus 5x squared plus 1 squared. All right? I just applied the formula. So what do I obtain? I'm just going to regroup. So actually the denominator, I'm not going to touch it. And I'm going to regroup the terms with respect to the powers here. So I will get x10 here, 3 plus 7, it's 10. And I will get 12 minus 21. 12 minus 21, it's minus 9. What do I have next is the power 5, because 3 plus 2 is 5. So I get x5 and I get 60, because 12 times 5 is 60, 60 minus 30, which is plus 30. And the last term that I have is 12x to the third. All right, that's it. That's it. Any questions? Okay, so let's move. B, C, D, E. Oh, so E, let's talk about the exponential. So the next section, next lecture, we will see more in detail this function. So the exponential is now quite often used in real world, meaning that when something is growing very fast, you say that it's increasing exponentially. So yeah, that's the exponential. And why we say that? Because that's true. This is the graph, the growth graph of the exponential. So exponential of 0 is 1. At minus infinity, it goes to 0, and it grows actually very fast. Right? It grows very fast. And so since it grows very fast, yeah, the common language has used this this coined expression of exponential increase, exponential growth. Okay, for example, at the beginning of an epidemic, it is known that often the increase is exponential at the beginning. Then when the virus, for example, has not too much people where it can go in, then it starts to fade out. Okay, so that's the exponential, and we are going to see it more in detail next time. But can you tell you so that uh, the derivative of exponential is the exponential? That's actually a way to define this function. That's the unique type of function such that the derivative are themselves. That's the exponential. Okay. I could, of course, add the number here. It will not change the thing. Okay. And so another function that we will see more in detail next time is the logarithm. And you can define, for example, the logarithm as the function such that the exponential of the logarithm of a real number x, it's x, right? So historically, we'll come back next time, but historically, so we call it also the Neperian logarithm, and it was introduced by Napier. Why? Because just a few words about the logarithm. For example, logarithm of 3 times 7 is log of 3 plus log of 7. So people back in the days, they didn't have computers, they didn't have calculators, so they had tables to when they dealt with complicated computations. They have a table so they can change the product into sums because sums are easier to deal with. And okay, so historically it comes from that. Okay, but what we are interested now is for a positive number x, so the logarithm is not defined for non-positive numbers. It's only defined for positive numbers. And so if I look at the derivative, I can tell you that the derivative of log of x, or ln of x, is 1 divided by x. Okay. Yeah, so this is just a few flavor, a small flavor, a glimpse of what we are going to talk about next week. So let's continue with other kind of functions. So that this will give you a relative large number of functions that you can derive. So another important kind of derivative, if let's assume that I have f of x, for example, that writes, for example, 3x squared plus 2x plus 2, and then I put it to the power fourth. Of course, we could develop that, and at the end of the day, this is a polynomial. At the end of the day, this will be a polynomial. However, there's a formula, you know, that, for example, f of x writes actually g of u of x with g of, you can write x if you want, or u, g of u is u to the fourth, and u of x is 3x squared plus 2x plus 2. And in fact, again, from the definition of the derivative, what we can deduce is that why is this here? Is that g, oh, Okay, g of u of x prime is actually g prime at u of x times u prime of x. Okay, so now if I apply that to my f of x, it will give me f prime of x equals 4. I'm computing here the derivative of g. The derivative g prime of u is 4u to the third. So, but I evaluate it at u of x. So it's 3x squared plus 2x plus 2 to the third times the derivative of this, which is 6x plus 2, right? All right. This is also an important computations for derivatives here, an important type of derivative. All right, let's finish with another few examples. So 7, let's look at the derivative of the cosine. Okay. Yeah, so cosine is a function that goes back to, that was very used in the Arabic world in the Middle Age. Okay, so but you can prove that the derivative of the cosine is actually minus sine of x. The derivative of sine of x is cosine of x. And the last example is, so here the tangent of x is defined by sinus x divided by cosine of x. And now I will use the formulas of derivatives to compute this function. So tangent prime of x is by definition is, so the derivative of sine, which is cosine, times cosine, so cosine square, minus sine times the derivative of cosine, which is minus cosine, which is plus sine square, divided by cosine square. Okay, I just use the derivative of the quotient of two functions. And so this one, I can write it, for example, either 1 plus tan square, or I could also do, because the cosine square plus sine square is always 1. This is also equal to 1 divided by cosine square of x. So that's the last example that I wanted to give to you. Of course, this is infinite. You can do these computations. Oh, actually, no, I have a couple more. I forgot. I have 2 more examples, but yeah, you have a lot of so you can do a lot of computations. So yeah, because I essentially talk about polynomials, cosine, sine, exponential, logarithm. I have 2 more examples that I wanted to share with you. I added it at the end. That's what I forgot. But anyways, f prime of x equals square root, for example, of 1 plus x squared. So we did see as an example the derivative of the square root. And now if I look f prime of x, so the derivative of square root is 1/2 of 1 plus x squared at the power minus 1/2 times 2 of x, which is times 2x. 2x is the derivative of 1 plus x squared. So this gives me x times 1 divided by square root of 1 plus x squared, which is x divided by square root of 1 plus x squared. Okay, and the last example is what is just now, let's assume that I want to compute the limit as x goes to 0 of sine of x divided by x. So here, what's the trick is that, so I gave you formulas and we did computations that rely on the definition of the derivative. So from the definition of the derivative, we deduced formulas from derivative of functions. Now, sometimes it's useful to do the other way, meaning that assume that I have this this limit to compute. So so the sine of 0 is 0, and so in fact this limit is 0 divided by 0, but I don't know what's this. And so there's several ways to compute that, but an interesting way to do that is to observe that this is also the limit as x goes to 0 of sine of x minus sine of 0 divided by x minus 0. So in fact, this is exactly the definition of, in fact, the derivative of the sine function at 0. But the derivative of the sine function is just the cosine function. So you can deduce that this limit is in fact 1. Right? So that's a trick. All right, so now we're almost done for today. The last thing, so I went from letters to numbers with the, so we can correct that. This is F, this is G, this is H, this is I, and this is J, and this is K. Okay, now the number 5, I just want to again give you a glimpse of what is called the Taylor formula. And this is the idea. So this is an important thing, actually, in modern calculus. This is an important thing in calculus. There are different ways to see it, but the main idea, so is that so let's assume that you have a function f of x. You want to approximate f. So you are here, so here you have f of a, and let's draw here the tangent. the tangent line to F. So the equation for the tangent is f of I plus f prime of A, so f of A plus f prime of A x minus A. And this, in fact, gives you, when x is small, this formula, this tangent, gives you an approximation of f. They're close. When x is small, if you call it, let's say g of x, this one, for x close to a, in fact, f of x and g of x are close. Okay, so the first approximation actually of f of x when x is close to a is f of a. When you add this term, you do better. You have a better approximation. So, but you could continue. You could do it again and again. So, for example, so to do that, I need to introduce these notations. Is, for example, f second here of a is by definition f prime of, is the derivative of the derivative of f at the point A, and f third, which we denote also by f third like that, is just the derivative of the derivative of the derivative of f at the point A. Okay, so you can go like that again and again. And what is called the Taylor formula is that you can approximate f of x by f of a plus f prime a x minus a, plus, if I want to take into account the second derivative, x minus a squared divided by 2 plus f third a divided by factorial 3 x minus to the third, and you could go again and again until the derivative of order n of a divided by factorial n x minus a to the n. And so when x is close to a, this is a good approximation of f. So there's various ways, in fact, to see it, to prove that it's a good approximation, but this is beyond the scope of these lectures that we are seeing. And so this is the main idea of Taylor formula. So that's it for today. If you have any questions, we'll be pleased to answer. If not, I just see you next week. All right, so bye-bye.